welcome to this problem walkthrough. Today, we'll be exploring problem number 802, titled Find Eventual Safe States. In this problem, we'll investigate how to determine the nodes in a directed graph that are considered eventually safe. Stick around as we dive into the problem, break down the approaches, and analyze the solution step by step. Let's get started. In this problem, we are tasked with finding the eventual safe states in a directed graph. The graph is represented as a list of n lists, where each list graph, I, contains the nodes that node I points to. A node is considered a terminal node if it has no outgoing edges, meaning its corresponding list in the graph is empty. Now, a node is defined as eventually safe if, starting from that node, every possible path either ends at a terminal node or reaches another eventually safe node. The goal is to return an array containing the indices of all the eventually safe nodes, sorted in increasing order. The input format includes the graph as a list of lists, and the output should be a sorted list of integers representing the safe nodes. For example, consider the input graph 1 2, 2 3, 5, 0, 5, The output for this graph is 2 4 5 6. Let's break this down. Nodes 5 and 6 are terminal nodes because they have no outgoing edges. Node 2 is eventually safe because it leads to node 5, which is a terminal node. Similarly, node 4 is eventually safe because it also leads to node 5. On the other hand, nodes like 0, 1, and 3 are not safe. Node 0 leads to a cycle involving nodes 1 and 3. Similarly, nodes 1 and 3 are part of cycles themselves, which disqualifies them from being eventually safe. In another example, with the input graph 1 2 3 4, 1 2, 3 4, 0 4, the output is 4. Here, node 4 is the only terminal node, as it has no outgoing edges. Nodes 0, 1, 2, and 3 are not safe because every possible path starting from these nodes eventually leads to a cycle. The problem also comes with several constraints and edge cases to consider. For instance, in a graph with no edges, all nodes are terminal and therefore safe. A graph with only one node is also trivially safe. Other cases include large cycles, disconnected components, and very large graphs near the constraint limits, such as when n equals 10,000. These scenarios require careful handling to ensure correctness and efficiency. To solve the problem of finding eventual safe states, we first consider a brute force approach using depth-first search, or DFS, for every node. The main idea here is to explore each node and check if it eventually leads to a cycle. If a node is part of a cycle or leads to one, it is deemed unsafe, otherwise, it is safe. In terms of implementation, we maintain a visited set that keeps track of nodes already traversed during the DFS from a single starting node. If we encounter a node already in this visited set, it indicates a cycle, and the node is marked unsafe. However, this approach has significant inefficiencies. The time complexity is O(n) squared, in the worst case because we perform a DFS, which can take O(n) time, for all n nodes. Additionally, the space complexity is O(n), due to the recursion stack and visited set. The major drawback is that this method involves repeated calculations for overlapping subproblems, such as revisiting nodes that have already been determined to be safe or unsafe. This redundancy makes the approach inefficient for larger graphs. To address the inefficiency of the brute force method, we turn to an optimized approach involving topological sorting with a reversed graph, using Kahn's algorithm. The key insight here is that a node is safe if it has no outgoing edges or if all its outgoing edges point to other safe nodes. By reversing the graph, we shift our focus to incoming edges, which allows us to easily identify terminal nodes, those with no incoming edges. The implementation involves four main steps. First, we reverse the graph by creating a new adjacency list where all edges point in the opposite direction. Next, we compute the integrity of each node in this reversed graph. Then, we use a queue to perform a topological sort, starting with nodes that have an integrity of 0, which are the terminal nodes. Finally, as we process the graph, we gradually remove nodes, marking them as safe once all their dependencies are resolved. This approach is highly efficient, with a time complexity of O(V plus E), where V is the number of nodes and E is the number of edges, and a space complexity of O(V plus E), for the reversed graph and integrity array. The key advantage is that every node and edge is processed exactly once, avoiding redundancy. Another optimized approach we can use is DFS with memorization, which builds on the brute force DFS by addressing its inefficiencies. The intuition remains similar. We explore each node to determine whether it is part of a cycle or leads to safe states. However, we use memorization to avoid redundant work. Specifically, we maintain a state array for each node, where 0 represents unvisited, 1 represents visiting, and 2 represents safe. During the DFS, when a node is visited, we mark it as visiting, and if we encounter it again in the same traversal, it indicates a cycle, and the node is marked unsafe. Nodes are marked safe once we confirm they lead only to other safe nodes or terminal nodes. This approach is both time and space efficient, with a time complexity of O, V plus E, since each node and edge is visited at most once, and a space complexity of O, V, for the recursion stack and state array. The memorization ensures that we never revisit nodes unnecessarily, making this method straightforward to implement while still being highly efficient for large graphs. After evaluating the different approaches, we chose DFS with memorization as the strategy for solving this problem. There are several key observations that make this method effective. Nodes can be classified into 3 categories: terminal nodes, which are safe, cyclic nodes, which are unsafe, and transient nodes, which are still being processed. The state of any given node depends solely on the states of its neighbors. By leveraging this dependency, we use memorization to avoid redundant calculations, significantly improving efficiency. The aha moment here is recognizing that assigning states and reusing results allows us to eliminate the need to restart the DFS for every node. This approach balances simplicity, efficiency, and scalability. Although the topological sorting method is equally efficient in terms of time complexity, DFS with memorization offers a simpler and more intuitive implementation, which is particularly useful for handling edge cases such as disconnected graphs and self-loops. The brute force approach, on the other hand, is computationally expensive and does not scale well for larger graphs, making it unsuitable for this problem. Overall, DFS with memorization provides the best balance for solving the problem effectively and efficiently. The problem we're tackling is to identify the nodes in a directed graph that are safe. A node is considered safe if, regardless of the path you take from that node, you will never encounter a cycle. To solve this, we can use a brute force approach involving depth-first search, or DFS, on every node. The idea is to explore each node and determine whether it eventually leads to a cycle. If it does, the node is deemed unsafe, otherwise, it's safe. To start, we represent the graph as an adjacency list, where each node points to its neighbors. For example, if U points to V, graph U will contain V. Additionally, we define N as the number of nodes in the graph. To aid in our traversal, we assign 3 states to each node. These will help us track whether a node is unvisited, currently being visited, or fully processed as safe. Let's look at the details of how these states work and how we iterate through the nodes. The 3 states we use for nodes during DFS are as follows. 0 means the node is unvisited, 1 indicates the node is currently being visited as part of the ongoing DFS path, and 2 signifies the node has been fully processed and is confirmed to be safe. With this in place, we can iterate over all the nodes in the graph, from 0 to N1, and apply the DFS logic to determine their safety. During the DFS for a node I, if the node is already marked as 2, we know it's safe and can return true. If it's marked as 1, this means we've detected a cycle, so we return false. Otherwise, we mark the node as 1 to indicate it's currently being visited. For each neighbor of the node, we recursively perform DFS. If any neighbor leads to a cycle, we mark the node as unsafe and return false. If all neighbors are processed without detecting a cycle, we mark the node as 2, confirming it's safe, and return true. Finally, after processing all nodes, we collect the ones marked as 2 and return them as the list of safe nodes. The core of this algorithm lies in detecting cycles efficiently. By marking nodes as 1 during DFS, we can immediately identify when a cycle is encountered. This allows us to terminate further exploration from the current node as soon as a cycle is detected, saving computation time. Additionally, marking nodes as safe with state 2 introduces memoization. Once a node is confirmed safe, it doesn't need to be revisited in future DFS calls, significantly reducing redundant calculations. In terms of complexity, this approach is highly efficient. Each node and edge in the graph is visited at most once, giving us a time complexity of O, V plus E, where V is the number of vertices and E is the number of edges. The space complexity is O(V), which accounts for both the recursion stack and the state tracking array. These optimizations highlight the effectiveness of using a state-based system and solving this problem. To implement this algorithm, we rely on three key data structures. First, we use an adjacency list called graph to represent the directed graph. This structure allows us to efficiently store and access the outgoing edges for each node. Second, we maintain a states array to track the visitation status of each node, with values of 0-4 unvisited, 1-4 visiting, and 2-4 safe. Finally, we use a result list to store the nodes that are determined to be safe, which will be our final output. To understand how these components work together, let's walk through a concrete example. Suppose the input graph is represented as 1 2, 2 3, 5, 0, 5, comma. This means node 0 points to nodes 1 and 2, node 1 points to nodes 2 and 3, and so on. We'll now go step by step to see how the algorithm processes this graph to determine the safe nodes. Let's start the DFS from node 0. From 0, we visit node 1, then node 2, and finally node 5, which has no outgoing edges. Since node 5 is terminal and doesn't lead to a cycle, we mark it as safe and backtrack. Now, we confirm that nodes 2, 1, and 0 are also safe, as they do not lead to any cycles. Next, we move to node 3. From 3, we visit node 0, which is already marked as safe. This confirms that node 3 is also safe. For node 4, we visit node 5, which is already safe, so node 4 is marked safe as well. Finally, nodes 5 and 6 are terminal nodes with no outgoing edges, so they are inherently safe. The result is the list of safe nodes, 2, 4, 5, 6. This walkthrough illustrates how the algorithm efficiently determines safety by leveraging state tracking and early termination when cycles are detected. To solve the problem of finding eventual safe states, we start by importing the necessary module and defining the eventual safe nodes function. The input is a directed graph represented as an adjacency list. First, we determine the number of nodes in the graph and initialize two structures, an out_degree list to track the number of outgoing edges for each node, and an incoming_edges list to store the reverse graph, where each node keeps track of nodes pointing to it. Next, we construct the reverse graph and calculate the out degrees by iterating through the input graph. For each node, we set its out degree as the number of neighbors and populate the incoming edges for its neighbors. Afterward, we initialize a queue to process terminal nodes, which are nodes with an out degree of 0. These nodes are inherently safe since they lead to no other nodes. Finally, we define a safe list initialized to false for all nodes, which we will use to mark nodes as safe during the processing. In the next step, we process nodes in reverse topological order using the queue. While the queue is not empty, we retrieve the current node, mark it as safe in the safe list, and then examine its incoming edges. For each parent node in the reverse graph, we decrease its out degree by 1, as one of its outgoing edges has now been processed. If the out degree of a parent node becomes 0, it is added to the queue since it has no remaining outgoing edges and can now be considered safe. Finally, once all nodes have been processed, we return a sorted list of the indices of nodes marked as safe. This ensures we provide the result in the required format, listing all the eventual safe nodes in ascending order. Here, we start by defining our method eventual safe nodes, which takes a directed graph represented as an adjacency list. The first step is to set up some essential variables. We initialize out degree, an array that tracks the number of outgoing edges for each node, and incoming edges, a reverse graph structure where each node maintains a list of nodes that point to it. Next, we populate these structures. For every node in the graph, we calculate its out degree by counting its direct neighbors. At the same time, we update the reverse graph by adding the current node as an incoming edge for each of its neighbors. This step allows us to focus on the reverse relationships in the graph, which is crucial for identifying safe nodes later. Lastly, we prepare for the next step by initializing a queue to hold terminal nodes, nodes with 0 outgoing edges. Now we move to processing the graph. Terminal nodes, which we added to the queue earlier, are inherently safe. Using a breadth-first search approach, we process these nodes in reverse topological order. For each node we dequeue, we mark it as safe and then reduce the out degree of its parent nodes in the reverse graph. If any parent's out degree becomes 0, it means that parent is now a terminal node and can be added to the queue. This process continues until the queue is empty. By the end of this loop, we've effectively identified all the nodes that can eventually lead to terminal nodes, marking them as safe. Finally, we prepare our result by iterating through all nodes and collecting those marked as safe. These nodes are added to the result list in sorted order, ensuring the output meets the problem's requirements. With the algorithm complete, the function returns the result list containing all eventual safe nodes. This list represents nodes that do not participate in any cycles and are guaranteed to either terminate or lead to termination. The implementation is efficient, leveraging a reverse graph and out degree tracking to solve the problem in a systematic and scalable way. This concludes our Java implementation for finding eventual safe states. To solve the problem of finding eventual safe states, we need to determine which nodes in a directed graph will always lead to terminal nodes, regardless of the path taken. Terminal nodes are those with no outgoing edges, and any node that leads to these without entering a cycle is considered safe. The solution involves a reverse graph traversal combined with topological sorting, where we leverage the out degree of nodes to identify and process terminal nodes first. In the given example, the graph has 7 nodes, and we start by calculating the out degrees for each node. For instance, node 0 has 2 outgoing edges pointing to nodes 1 and 2, so its out degree is 2. Similarly, we calculate the out degrees for all nodes, and nodes 5 and 6 are identified as terminal nodes since their out degree is 0. This sets the foundation for our approach, where we work backward from these terminal nodes to find other safe nodes by reducing their neighbors' out degrees. Next, we construct the reverse graph, where the direction of each edge is flipped to point back to its parent nodes. For example, node 2 in the original graph has outgoing edges to nodes 5 and 6, so in the reverse graph, nodes 5 and 6 will have incoming edges from node 2. This reverse graph helps us track which nodes depend on others. We initialize a queue with terminal nodes, in this case, nodes 5 and 6, and begin processing them. First, node 5 is marked as safe, and its parents, nodes 2 and 4, have their out degrees reduced. If any parent's out degree becomes 0, it is added to the queue as a new terminal node. After processing node 5, we move to node 6, marking it as safe. As node 6 has no parents, the queue now contains nodes 2 and 4, which will be processed similarly. This iterative process ensures that we propagate the safety of terminal nodes backward through the graph. Processing continues with node 2, which is marked as safe. Its parents, nodes 0 and 1, have their out degrees reduced, and if any of them becomes 0, they are added to the queue. Following this, node 4 is processed and marked as safe. Similarly, node 0 is processed next and marked as safe, leaving only node 1 in the queue. Finally, node 1 is processed and also marked as safe. At this point, all nodes that lead to terminal nodes without entering a cycle are identified as safe. The result is stored in a Boolean array where each index represents a node, and the value at that index indicates whether the node is safe. For this example, the safe nodes are nodes 0, 1, 2, 4, 5, and 6. Sorting these nodes gives us the final output as a list, 0, 1, 2, 4, 5, 6. To reinforce this process, consider the second example graph with 6 nodes. Here, we initialize the out degrees, reverse graph, and queue with terminal nodes, which are nodes 3 and 5. Processing begins with node 3, marking it as safe and reducing the out degrees of its parent nodes. Node 5 is then processed similarly. Next, node 2 is processed, marked as safe, and its parent node's out degrees are updated. This pattern continues with nodes 1 and 0, which are processed in turn and marked as safe. The resulting safe nodes are 0, 1, 2, 3, and 5. These nodes are sorted to produce the final output, 0, 1, 2, 3, 5. This example further highlights the effectiveness of using a reverse graph and out degree reduction to propagate safety backward through the graph, ensuring all eventual safe states are correctly identified. The efficiency of this algorithm comes from its reliance on fundamental graph properties. The time complexity is O, V plus E, where V is the number of nodes and E is the number of edges, as each edge is processed only once. The space complexity is also O, V plus E, since we store the reverse graph and use a queue for processing. This approach systematically identifies safe nodes by leveraging the reverse graph, out degree reduction, and topological order. By propagating safety backward, we ensure correctness and compliance with the problem's requirements. Finally, sorting the safe nodes as the last step guarantees the output is in the desired order. This combination of efficiency, clarity, and correctness makes the solution robust and well suited for this problem. To analyze the time complexity of our solution, let's break it into distinct steps. First, we build the reverse graph and calculate the out degrees for all nodes. Iterating through the input graph takes O, n, where n is the number of nodes, and for each node, iterating through its neighbors takes O, e, where e is the total number of edges. Combining these operations, this step has a complexity of O, n plus e. Next, we initialize the queue with terminal nodes. This involves iterating through the out degree array, which requires a single pass over all n nodes, taking O, n. Finally, we process the nodes in reverse topological order. Each node is added to the queue and processed exactly once. Additionally, for every node, its incoming edges are traversed, and their out degree values are decrement. Since each edge is processed exactly once across the graph, this takes O, e. Appending and popping nodes from the queue also takes O, n, as each node is enqueued and dequeued once. Altogether, this step has a complexity of O, n plus e. Once the reverse topological processing is complete, we construct the output list of safe nodes. This involves iterating through the safe array, which is of size n, and thus takes O, n. Now, summing up the complexities of all the steps, we have O, n plus e, for building the reverse graph, O, n, for initializing the queue, O, n plus e, for processing nodes, and O, n, for constructing the output. Combining these terms gives us a total time complexity of O, n plus e. This is highly efficient for graph representations where the graph size is proportional to n plus e, such as adjacency lists. Moving on to space complexity, the graph representation itself requires O, n plus e, space, as it's stored as an adjacency list. Additionally, we use auxiliary arrays. The out degree array, which tracks the out degree of each node, takes O, n, space. Similarly, the incoming underscore edges array, which stores the reverse graph, also takes O, n plus e, as it mirrors the structure of the original graph. We also use a Boolean array, safe, to track which nodes are safe. This array is of size n, so it takes O, n, space. On top of that, we use a queue to store nodes during the reverse topological sort. In the worst case scenario, all n nodes could be enqueued, requiring O, n, space for the queue. Combining all these memory components, we have O, n plus e, for the graph and incoming underscore edges, O, n, for the out degree array, O, n, for the safe array, and another O, n, for the queue. Adding these together, the total space complexity is O, n plus e. This is efficient for both sparse graphs, where the number of edges is much smaller than the number of nodes, and dense graphs, where the number of edges approaches n superscript 2. Comparing this to a naive approach, a less optimized solution might involve recursively exploring all paths from each node to determine if a cycle is reached. This could result in an exponential time complexity, O, 2 to the power of n, where the number of paths grows exponentially with the number of nodes. Our current implementation avoids this by leveraging reverse topological processing and ensuring each node and edge is processed only once. This optimization reduces the time complexity to O, n plus e. To better understand the efficiency, let's consider the best, average, and worst cases. In the best case, a graph with no edges, where all nodes are terminal, requires only O, n, time, as no edges need to be processed. For an average case, like a sparse graph with a typical distribution of edges, the time complexity remains O, n plus e. In the worst case, a dense graph where every node is connected to every other node results in O, n superscript 2, time complexity due to the maximum possible number of edges, which is n superscript 2. To prove our big O analysis, note that each node is processed once in the queue, taking O, n, and each edge is processed once during the reverse graph traversal, taking O, e. Adding these gives O, n plus e, which matches our earlier calculation. Similarly, space complexity is dominated by the graph representation and auxiliary structures, leading to O, n plus e, memory usage, making the solution efficient in both time and space for a wide range of graphs. When solving the problem of finding eventual safe states, there are several common mistakes to watch out for. First, not marking nodes as visited during a depth-first search can lead to infinite recursion or redundant computations. This happens because the algorithm might repeatedly explore the same nodes, especially in cycles, significantly increasing the time complexity. To avoid this, you should always use a visited set or a state array to track nodes that are currently in the recursion stack. Another mistake is confusing cycle detection with pathfinding. Detecting cycles requires checking if a node is revisited in the current DFS path, which is different from simply determining if a node is reachable. If you apply standard pathfinding algorithms like BFS or DFS without modifying them for cycle detection, you're likely to get incorrect results. Finally, using the wrong graph representation can also cause inefficiencies. For sparse graphs, an adjacency list is much more efficient than an adjacency matrix, which uses n² memory and can slow down traversal unnecessarily. Always choose the representation that matches the problem's constraints and graph density. Another frequent pitfall is forgetting to handle edge cases. For example, if the graph is disconnected, includes self-loops, or has no cycles at all, your solution might break if these scenarios are not explicitly accounted for. Consider a graph with just a single node and no edges. This should be treated carefully to avoid false positives in cycle detection. Additionally, if the problem requires answering multiple queries, such as checking whether various nodes are safe, failing to pre-process results can lead to redundant computations. For example, if you determine a node's safety status but don't store the result, you might end up traversing the graph repeatedly for each query, which significantly increases the time complexity. To handle this efficiently, you can use memoization to save the results of previously processed nodes and reuse them as needed. When approaching graph problems in interviews, it's important to recognize that many of them boil down to identifying cycles or paths within the graph. Mastering techniques like DFS, BFS, topological sorting, and union find will give you a strong foundation. For problems involving cycles, maintaining distinct states for nodes such as unvisited, visiting, and visited can help you detect cycles efficiently. If you're tasked with finding safe nodes, one useful trick is to reverse the graph and analyze it backward. For example, a reverse DFS or topological sorting can simplify the problem by focusing on terminal nodes first. Additionally, if you're dealing with multiple queries, pre-processing the graph and memoizing results for nodes already determined to be safe is a great optimization. Interviewers may also ask follow-up questions, such as how your solution would handle very large graphs with hundreds of thousands of nodes or how it could be adapted to handle dynamically added nodes or edges. Be prepared to discuss scaling and dynamic updates in your approach. There are several related problems that share similar concepts with the eventual safe states problem. For instance, LeetCode 207 and 210, both centered on course scheduling, involve cycle detection in directed graphs. Similarly, problems like LeetCode 785, which checks if a graph is bipartite, or LeetCode 547, which counts the number of connected components, focus on graph traversal techniques. Exploring these problems will deepen your understanding of graph algorithms and their variations. Now, let's discuss alternative approaches. One option is topological sorting, where you iteratively remove nodes with no outgoing edges to identify cycles. This approach works intuitively for acyclic graphs but may be less efficient for dense graphs with many cycles. Another approach involves reversing the graph and then performing BFS or DFS to identify nodes that lead to terminal nodes. While this method simplifies the problem in some cases, it requires additional space to store the reversed graph. It's important to weigh these trade-offs when selecting your approach. Another approach worth considering is using union find, also known as the disjoint set union algorithm. This method is particularly effective for detecting cycles and classifying nodes in undirected graphs. However, applying it to directed graphs is more challenging due to the complexities introduced by path direction. For example, you must carefully manage path reversal and ensure that cycles are detected accurately in the directed case. While union find can be highly efficient for undirected graphs, its implementation for directed graphs is more intricate and may not always be the best choice. Understanding these trade-offs will help you decide when this approach is appropriate for a given problem. Great job making it to the end. In this session, we explored problem number 802, broke it down step by step, and applied DFS to find the eventual safe states. The key takeaway here is the importance of understanding graph traversal techniques, especially for problems involving cycles. Thanks for watching, and don't forget to like, subscribe, and keep practicing. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!